Hi guys, so this next unit is all about the periodic table, and you'll notice that the periodic table we gave you for honors has a lot less information on it than the periodic table and the reference tables that you have in the Regents reference table packet. So we're going to go through how the periodic table is organized and some things that are important for you to know about where the elements are. I posted a copy of the note packet and the worksheet packet in a new topic in Google Classroom. So whether you want to print, maybe print the note packet out if you can. You can print multiple sides on a page so that you don't waste a lot of paper. You could also print on both sides. So I would print the note packet, maybe the worksheet packet. You can just do it in Google Docs, but at least I would have this to write on throughout this unit. Okay, so I wanted to start off by showing you guys a little TED Ed video, and I just think it explains nicely why the point of putting the periodic table together, like why we put the elements in this sort of chart. Okay, so let's just watch this.
The periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitry Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really, that had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitry was making a bold statement. He said, and I'm paraphrasing here, y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time. Scandium, germanium, rhenium. The element he called Eka-manganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitry predicted its existence, 30 years after he died. Dmitry died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.
Okay, guys. So I just think that video introduces it so nicely. How Mendeleev organized the elements on the periodic table was actually by atomic mass. Currently, the elements changed a little bit in order. So the modern periodic table, which was designed by Moseley, and his name is not so important, really. You're asked about Mendeleev more. For the current periodic table, they'll ask you how's the modern periodic table organized. Today, it's organized by atomic number. And you might think, well, as atomic number goes up, mass goes up, so it's the same thing. There are a few exceptions on the table where something has a higher atomic number but a lower mass. So just at the time when Mendeleev was organizing the elements, they really didn't discover subatomic particles yet, number of protons, atomic number. So this is the order that they're in today. But why Mendeleev was famous? It was so special that he was able to say, well, there's an element that exists that you guys didn't find yet, and you're going to find it one day. And when you find it, it's going to be like this, this, and this. And he was right. Every prediction that he made about missing elements on the periodic table were later discovered, and the properties that he predicted were correct. So he was the first scientist to put the elements in a chart like this and say, well, when they're organized this way, we're going to know things about the elements just based on where they're placed. And that's important for you guys too. There are going to be a lot of elements on this table that you've never heard of before, you've never seen in real life. But by the end of this unit, you're going to be able to tell me something about those units just based on what row and what column they're in on the periodic table. So that's pretty cool. So the modern periodic law, what it says is properties of elements are periodic functions of their atomic number. And all that means is that when the elements are in atomic number order, there are patterns. Like properties of the elements, they repeat as you go down the periodic table. And that's why we're able to make those predictions and say things about elements that we've never actually seen before. So that's pretty cool. Talking about some of the elements, and I talked to some of you in class about this in the atom unit when you guys were studying your elements and your symbols. Sometimes this symbol and the element itself don't match up. And that's because a lot of the first elements that were discovered, their symbols were given based on their Latin names. So copper doesn't have a U in it, but cuprum does, which is its Latin name. Lead is my favorite, PB for plum bum. Okay, that's what it is in Latin, and I'm probably pronouncing it horribly, but that's okay. So this is just a cool little chart to look at. Okay, so as far as organization goes, the first thing we talked about how they're in atomic number order, but what made the scientists make 18 columns, and what made them make 7 rows? Like, how did they come up with these numbers or these dimensions for the table? The first thing we're going to talk about are groups or families, and the groups are the vertical columns. So my up and downs. And if you count the columns on your periodic table, there are 18 of them. On the Regents reference tables, they're actually numbered up here, and there are 18 of them, so you can see that. So what's important about elements that are in the same group, if you look at your Regents reference table, The electron configuration is telling you how many electrons are in each electron shell. Okay, so if I look down group 1, I notice that every electron configuration ends in the number 1. If I look down group 2, every electron configuration ends in the number 2. So if they're in the same group, that means that they have the same number of valence electrons. And guys, you're not given electron configurations on your periodic tables, but you do know how to write out electron configurations, and you can figure out how many valence electrons are in each group. In the next unit, it's going to be more important that you're able to do that quickly. So I'll show you how to figure it out a little bit quicker than writing out the whole configuration. But for now, you just have to know same group means same number. Because they have the same number of valence electrons, they're going to react in similar ways. They're going to have similar chemical properties. Now, the goal of every element on the periodic table is to be stable. Stable means that the valence electron shell has 8 electrons in it. So if the valence electron shell does not have 8 electrons in it, the atom is going to do something to get 8 valence electrons. So if they have the same number of valence electrons to begin with, they have to do the same thing to get to that final number of 8. So they have similar chemical reactions if they're in the same group. As far as our periods go, our periods are our horizontal rows. So they're called periods. Okay. And guys, again, on the Regents reference tables, the periods are numbered here on the side. Your reference table is not numbered for you, but you can absolutely write numbers in if you want. But there are 7 rows. And the period number is the same as the number of electron shells, or we call them principal energy levels. Either way is okay. Right. So how do we know that? And again, guys, for you, it's going to just be easier to remember that the period number equals the number of shells. But if you had your Regents reference tables out, if I look at the electron configuration, see how calcium has 4 numbers in it, 2882? That is telling us how many electrons are in each ring. So if there's 4 numbers, there's 4 rings or 4 shells. And every single element in the 4th row has 4 numbers in its electron configuration. Same thing with the 5th row. Everything in the 5th row has 5 numbers in its electron configuration. So that's another thing that's worth you guys remembering. The last thing we're going to talk about today are these bottom 2 groups of elements that are hanging off the periodic table at the end. And we talked a little bit about this in the atom. So these are called, the top is called the lanthanide series. And the bottom row is called the actinide series. And the series, guys, is just named after the element that the series starts with. So if you look at element number 57 and 89, those are the names of them, and just the elements that come after them. So all you really need to know about these elements, guys, is that they're very rare, and it's where the F block fills up. Okay, so this is this comes from period 6. We just kind of took it out and put it down here, and this comes from period 7. And we took it out and put it down here so that all of the rest of our columns would line up. That's all you have to know about them. Nothing really too much. Finally, guys, you do need to know the phases of the different elements at STP. And STP is standard temperature and pressure. And for the sake of like putting a number on this, 0 degrees Celsius or 273 Kelvin is standard temperature. So it's not room temperature. It's actually 0 degrees Celsius. Water would be freezing at standard temperature. In your Regents reference tables, you're given the melting and boiling points of all the elements. So you can go ahead and compare the temperature of the air to its melting and boiling point and figure out if it's a solid or a liquid or a gas. For you guys, you don't have that chart available to you until you take the Regents at the end of the year. So this is another thing that you have to remember. The gases are the toughest to remember because there's just like a couple of them. So hydrogen is a gas, nitrogen, oxygen, fluorine, chlorine, and all of group 18. Those are all gases at STP. The liquids, there's only 2 of them, mercury and bromine. Only 2 elements that are liquid at STP. If you guys can remember what the gases are and what the liquids are, everything else is a solid. Okay. So to kind of help you make sense of this, and I don't want you guys to write this down on this slide because we're going to write something else on this slide, but I just want to show you like a pattern. If you take your pen and you make a number 7, and then you take your pen and you make a little number 7, those are all the gases. So an outer 7 and an inner 7 are all of the gases at STP. Then if you can just remember liquid, liquid, everything else is a solid. Okay? So guys, in our next video, we're going to talk a little bit more about different ways that the elements are grouped together so that you can actually know a little bit more about them than you even think. I'm going to give you some questions to answer, and we'll talk more tomorrow. Thanks, guys.